Hi everyone, this is the video for Monday night, March 1st. I'm sorry I can't be with you in person to go through this with you, but I will be holding office hours on Tuesday from 6 to 7 o'clock in Blackboard Collaborate, and I'll make sure to send out a link via email to you guys on Tuesday for that. So if you do have any questions about any of the material that I go over in this video, you can pop in and I can recap any of it with you one more time before our meeting on Wednesday. All right, so this lesson is about quadratic functions, and we're going to start with a function that is in what we call standard form, where we say a is the number in front of the x squared, b is the number in front of the x, and then c is the number that's all by itself there. To find the vertex, we're going to use a formula called negative b over 2a, or the opposite of b over 2a. The opposite of b means take your b and change the sign. So my b here is a positive 6. If I change the sign, it's going to be a negative 6. And then 2 times a, 2 times negative 2. So we're going to get negative 6 over negative 4. And then if I reduce that, I'm going to get either 3 halves, or we can just say 1.5, and that's going to make that one a little easier to graph. So we'll keep it as 1.5. That value is the x coordinate of your vertex. And when we're looking for a vertex, remember we're looking for a point. It's either the highest or the lowest point on these parabola graphs. So we've got the x coordinate, we need the y that goes with it. To get the y that goes with it, we don't need a formula. We've done this a lot in this class. If you have an x and you want to know the y that goes with it, you plug it into the function. So here we have function h. We're going to replace all the x's with 1.5. So it's going to be negative 2 times 1.5 squared plus 6 times 1.5 minus 3. And then all of that you can just type in the calculator. All at once is fine. And you can see we also get 1.5. So my vertex is the point 1.5, 1.5. And I'm going to go ahead and graph things as I go here. So 1.5, 1.5. It's going to be right about there if I count by ones on my graph. Axis of symmetry. Axis of symmetry is a vertical line that goes right through your vertex. It's always a vertical line. So these are always going to start with x equals. And because it goes through your vertex always, the x coordinate that we're looking for is the x coordinate of your vertex. So x equals 1.5. So again, you could use that formula, opposite of b over 2a, and that will also give you that axis of symmetry. So these two pieces kind of go hand in hand. Okay, next we want to know if this quadratic is concave up or concave down, has a min or a max, increasing, decreasing. I think I'm going to do this in a little bit of a backwards order here. I'm going to go ahead and graph it first, and then we'll come back and answer some of these other questions. To graph the function, we already have 1 point on the function. You can pick other points using an XY table. These graphs are symmetric, meaning they look the same on both the left and the right of our vertex point. So a good way to graph is to pick a value on the left and the right of our vertex. So you could say pick an x value of 0, perhaps on this graph. That would be to the left of my vertex. And then you could also pick an x value of maybe 3. That would be to the right of my vertex. And those values are the same distance away from my vertex, so we should expect to get the same number out twice if we're doing this correctly. To get the y's that go with those x values, we're going to do the same thing we did to get the second part of our vertex. We're just going to plug 0 into the function everywhere we see an x. So negative 2 this time times 0 squared plus 6 times 0 minus 3. So that's going to give me -3. We'll fill that in a moment. And then we're also going to plug in 3. And remember, we picked values that were the same distance from the vertex here, so we should be getting the same value twice. If you pick values that aren't the same distance from the vertex, though, no worries. You will still get 2 points that are on the graph, which is really all that matters here, so we can get a nice picture of it. So both of those evaluate to -3. And then we can plot those points, 0, -3, and 3, -3. We're going to connect these to make what we call a parabola shape. It's going to be a U. Be careful that your graph doesn't look like a V shape here. It's going to be rounded at the top. And then arrows at the end of it to show that it's going to go down forever. So when we say, is it concave up or concave down? Another way to say that is this graph opening up or down? This graph is what we call concave down because it's a upside down parabola versus a right side up parabola that looks more like a proper U, what we call concave up. Does it have a minimum or a maximum? Well, that means does it have a high point or a low point? This graph, the vertex is the highest point on the graph, this guy right here. So we have a maximum value versus a minimum value. Name the intervals where this function is increasing or decreasing. To do that, we're going to follow our graph, and it's important that you follow it from left to right. So we're going to start on the far left side of our graph, and as I trace, you can see that I'm going up, 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 until I get to my vertex. So as I go from left to right, we say that the left side of that graph is what we call increasing because the values are getting higher and higher. So now we want to list what those x values are. Those values go from -infinity, meaning the farthest value to the left that we could possibly have, all the way to my vertex. And my vertex, remember, was at 1.5. It's important when you list increasing and decreasing that you are using x values only. Okay, so from -infinity on my x-axis all the way to 1.5, this graph is increasing. Then the graph turns around and starts going down if I trace it, again, from left to right. So we say that this graph is decreasing from 1.5 all the way to positive infinity. So that's going to look very similar to the interval notation that we're used to there. Okay, next we're going to do domain and range, part F here. So this is just review from previous lessons. Remember, domain is all of your x values and range is all of your y values. This graph will go forever left and right as we extend my curved lines out there. So we say the domain is all real numbers. You could also look at the graph of this function, or the equation, excuse me, of this function, and see that there's no value for x that we wouldn't be allowed to plug in. I don't have any denominators with an x in them. I don't have any square roots, so we don't have any of those domain restrictions, which gives me a domain of all real numbers, and that's going to be the same for all parabolas. Then we want to talk about the range, our y values. This graph goes down forever. So we say it goes all the way down to -infinity. And then we want to see what that maximum value is, the highest y that it reaches. And remember, that's part of our vertex, 1.5. We do have a point at 1.5, so we want to make sure we include that as a square bracket instead of a parentheses. Remember, our infinities will always be parentheses. Finally, we want to estimate our x-intercepts. X-intercepts are any places where it's crossing the x-axis. And for right now, we're estimating, but later in this chapter, we'll be able to actually calculate those. So approximately, we're going to say +1 and maybe 2. We'll say for that one. But again, that's just an approximation of where it's crossing the axes. Okay, so that's problem number 1. Let's look at problem number 2. Problem number 2 is converting to vertex form. To do this, we're going to calculate the vertex. We're going to use that same formula we did last time. X equals the opposite of b over 2a. The opposite of b is a positive 6. In this case, remember a first, b second, c third, all over 2 times a, which again is also 6. So I have a 6 over 12, which is a 1/2. Then, to find the y that goes with that x, we're just going to plug that x value in, 1/2, or we can use 0.5 when we type it in the calculator if that makes it a little easier to find the y that goes with it. Okay, so let's go ahead and type that in. And again, I'm going to use 0.5, just a little easier to type. And I get 2.5. So my vertex is, we'll just use the decimals here because they're exact, 0.5, 2.5. So that's my vertex. That's the first thing we're going to do. Then we're going to actually put that in vertex form. So vertex form looks like this, where a is the same value of a we have in the original equation. We already had that labeled as a 6. And h and k are the x and y coordinates of your vertex. Don't forget to bring the minus in, so it's going to be x minus 0.5, or a 1/2 squared, plus 2.5. Okay, the last two questions, we want to know if this graph is concave up or concave down. And we don't necessarily have to graph the whole thing here. So a good way to tell that is you can look at the a value. If the a value of your equation, in either form of the equation, because remember it's the same a value both times, if a is a positive number, this graph will open up, or we say concave up. Or if a is negative, we say that it concaves down. Because a is a positive number in this equation, this graph will concave up. So you could almost make a little kind of rough sketch of it. My vertex is a 1/2, 2.5, and then we know it's going to concave up, so it's going to look something like that. Okay, and again, I'll label that point 1/2, 2.5, because that's going to help us with the last part, finding the range. So the range is either all the points below the vertex, or in this case, it's all the points above the vertex. And remember, it's our y's. So we're going to start at our vertex, and we're going to use that square bracket again. My y value of my vertex is 2.5. And then we know this graph will go up forever. So positive infinity. And you can get that without actually doing an XY table and plotting all the points. Just focus in on that a value. Okay. All right, let's move down to number 3. Got a word problem here we can practice with. I know everybody loves these, but the good thing is the equation's done for you, so that's helpful. It says your factory produces widgets. Each unit is cheaper the more you produce, but costs will eventually go up if you make too many due to the cost of storage. Your cost for producing X thousands of units, and let's underline that because that's going to make a difference maybe in our answer, can be approximated by the following formula. We want to find the daily production level that will minimize your costs. So a lot of times with a quadratic function, you're going to be asked to find a maximum value or a minimum value because they have these kind of curved shapes, and that max or min is that vertex. So when I see minimize, or if you see a problem that says maximize, it's really just asking you to calculate the vertex. Okay, so to do that, we're going to use the same formula we practiced already, opposite of b over 2a. Opposite of b in this problem, make sure I label them here, a, b, c, is positive 8.504, and then 2 times a, which is 0.04. Notice every time I'm doing this, I'm just plugging in the numbers in front of the x or the x squared. I'm not actually putting an x into this formula anywhere. All right, so let's go ahead and type that in our calculator, and let's see what that gives us. So 8.504 divided by, I'm going to do this all once here, 2 times 0.04. and we get 106.3. Okay, so that's the x value of my vertex. To get the y that goes with it, again, we're just going to plug it in. And actually, in this case, well, we can keep it a y, but remember, it's also our c value, our cost is what that represents in this problem. So we're going to do 0.04 times my x, 106.3 squared, minus 8.504 times my x, 106.3, and then finally plus 25302. And again, we can just type all that in the calculator. Okay, so we're going to do 0.04 times 106.3 squared minus 8.504, 106.3 plus 25302. Okay, and we get 24,850 approximately. I'll just round to the nearest whole number there. Okay, so find the daily production level that will minimize your costs. So the daily production level that's going to minimize my costs is that x value that we had a second ago. And remember that x value was in thousands of units. So when we say 106.3, it's 106,000. So you can move the decimal 3 spaces to the right to put something in thousands, because 1,000 has 3 zeros. It's a good way to remember that. So that many units will give us a minimum cost of, in this case, 24,850. So if they just needed how many units, your answer would be 106,300. Again, the decimal just moved 3 spaces over to account for thousands there. And then if they wanted to know what that minimum cost is, you have that as well from your vertex. Okay. One other thing I want to mention, we didn't do it in the graphing problem, but you can always check your graphs with the graphing calculator, or look at the graph in the graphing calculator if you're not sure if it's concave up or concave down, something like that. You can just go to your y equals, and you can type your equation in. So let's say I wanted to check this first one that we did a moment ago. It was negative 2x squared plus 6x minus 3, and I'll just hit graph. Actually, I don't know if I'm in my regular window, so I'm just going to hit zoom 6, and then you can compare that to the picture that we have. Another great thing you can do with this is you can go to your table of values. Ooh, I wanted to move that, not right on it. There we go. In your calculator, you can go to table, and you can get x and y values for your xy table and plot those if you don't want to fill those values in by hand. That can make it a little bit more efficient if you use your calculator for that part. Okay, so those were most of our big ideas from section 3.1, that Edpuzzle. So let's move on to the second Edpuzzle for this week, and that was section 3.4, which is just a little bit more with quadratic functions. So it says the following data can be modeled with a quadratic function. We want to find the equation that goes with it. All right, so to find the equation, the first thing we want to hunt for is our vertex. That's the most important point of a quadratic. And remember, a vertex is either a minimum or a maximum. So this is what it would look like if it was concave up, for example. And so what that's going to look like in a set of coordinates is a turnaround point, a point where my graph stops decreasing and then starts increasing again, or vice versa. You can also look for symmetry of values. So here you can see, like, I have a 5 and a 5, a 7.5 and a 7.5, 3.5 and 3.5, and then right in the middle, I have this guy right here, negative 1, 3. That point is where my y values turn around. They start decreasing all the way down to 3, and then from there they increase again. So my vertex is negative 1, 3. The other thing I need to be able to find an equation is an a value. And I think if it doesn't tell you what kind of equation you want to write, it is easier to write an equation in vertex form. If you were doing like MyMathLab and you needed an equation in standard form, you could always take this answer and you could FOIL it out, and that would give you an answer in standard form. That was in the 3-1 Edpuzzle. That's an option. But we already know part of this equation. We already know my h, remember that's the first part of my vertex, and the k, that's the second part of my vertex. So it's going to be x minus -1. Now you can write that, or you could just write, we know when it's minus and negative, it's going to be plus. And then I also know my k. So really the only part of the equation that I don't have that I need to find is the a value, because x and y we know stay in our equation. To find the a value, you can pick any point on this graph and plug it in for x and y. I'm just going to pick 1, 5. Looks nice and pretty, but any of the points listed here would work. My y coordinate is 5. My a is what we're going to be finding. My x is 1. Okay, and then we're going to do some order of operations here. So inside my parentheses first, 1 and 1 gives me 2 squared. 2 squared gives me 4. And then to solve for a, I'm going to subtract 3 on each side, which gives me 2 equals a times 4. And finally, if I divide by 4 on each side, I'm going to get 2 over 4, or 1/2. And that's enough to answer this question then. Y equals 1/2 x plus 1 squared plus 3. And then if you wanted to check it, a great way to do that would be to pick another point in this table, plug it in for x and y, and make sure that you get the same thing on both sides of the equation. That would be your check. Okay, so that's our final answer for that one. We find our vertex first was the step that we used to find h and k, and then we plug our vertex and another point in to solve for a. Again, if you needed an answer that was in the other form, you could always FOIL this out. And when I say FOIL, remember that's multiplying x plus 1 times itself. Then you can distribute and combine like terms to finish the problem. Okay. Let's move on to number 5. Here we're finding a parabola that passes through the following points. So we're given some points here, kind of like we were in the last problem, but I'm not given enough points to determine the vertex. I don't see those turnaround values at all here. So what we're going to have to do is create a system of equations. And it is easiest to do that if you don't know what the vertex is, using this standard form, ax squared plus bx plus c. It's helpful to remember in these equations, c is your y-intercept, or it's where you have an x value of 0. And so if you're lucky, like this one, we are given our y-intercept. So our c value is 4 in this problem. Again, because the point 0, 4 tells me I have an x-intercept. Okay, so we're going to go ahead and fill that in. From here, we're going to use the other 2 points to create a system. Okay, so we're going to use the point 1, 3 first, and we're going to plug 1 in for all my x's and 3 in for my y. In my equation, that would look like 3 equals a times 1 squared, and we'll finish and simplify that a little bit, plus b, I don't know what that is, again, times 1 plus 4. Okay. Let's do the same thing for that second point we had, 2, -4. So -4 goes in for my y, 2 goes in for each of my x's this time. There we go. Okay, and if I simplify each of those equations, let's say I start with this one at the top. I would have a times 1 squared, which is just 1a, or just a, plus b times 1, which is just b. And then one thing that you can do kind of all in one step here is you can take this 4 if you want and move it to the other side, or you can just leave it. It's not going to hurt anything. We'll just leave that there. And then you can do the same thing for the bottom equation. -4 equals, so we're writing this guy. If I do 2 squared, I get 4 times my a plus 2 times my b plus 4. Okay, and then we're going to solve for A and B. This looks like a elimination problem is how we've done most of these. You can use substitution here as well, but I like elimination, so I'm going to do that. I'm going to multiply my top equation by -4. So that would give me a -12, a -4a, a -4b, and a -16. Add those together. I have -16. My a's cancel. 2b and -4b give me -2b. 4 and -16 give me -12. Then to solve for b, I'm going to add 12 on each side. So -4 equals -2b. And then if you divide by -2 on each side, you're going to get b equals 2. Okay, so I had my c earlier, that's highlighted up there. I have my b, 2. Okay, and now let's go ahead and plug b back into either of those equations to solve for a. So let's say I use that top equation there. 3 equals, I don't know what a is. I know b is 2. I had that 4 there already. So 3 equals a plus 6. And if I subtract 6 on each side, I'm going to get a equals -3, which was the other piece we were looking for here. Okay, so now let's go ahead and write that final equation. Our final answer is y equals, we're going to fill my a in front of my x squared, my b in front of my x, and then the c, we knew that at the beginning. There is our final answer. If you want to check it, you can really easily do this with your graphing calculator, actually, or you can do this by hand as well. We're just going to type our equation in y equals, so hit y equals, clear out what you've got in there, -3x squared plus 2x plus 4, and then you can graph it if you want, but more importantly here we want to go to table, second table, and then we want to make sure that those original points we were given at the very top are included on this graph. So you can scroll up if you don't see them on yours, scroll up or down, but 0, 4, 1, 3, 2, -4, those are all points in this table, so I know that I have the correct equation. Okay, you could also, if you didn't have a graphing calculator, just plug in 0, 1, and 2, and make sure you get out the y's that go with them, respectively, 4, 3, and -4. Okay, last problem for this lesson is about quadratic regression. So linear regression is a line of best fit. Quadratic regression was introduced in this lesson. They talked about instead of first differences, second differences can be used to determine if a quadratic model would be appropriate. But we use quadratic regression when our data should be modeled with a curve that on one side is going up and on the other side is going down. So data that has a minimum or a maximum would be, in the most case, appropriately modeled with a quadratic regression versus a linear. So for this data, we're going to run a linear and a quadratic regression and determine which one is a better fit. So it's going to start out the same as what we did in the last chapter. We're going to go to Stat, and then we're going to go to Edit. And we're going to clear out what we've got in there. So we're going to go up to the list name, hit clear, go back down. Up to the list name, hit clear, go back down. And you can type in the actual years if you want. I like to use years after a certain year because otherwise your values are going to get really big. So let's say we're going to use, I don't know, years after 2000. And if you're doing this in my math lab, they'll be specific with that in the instructions already for you. So if I'm going to put in 2011, I would use 11 because it's 11 years after the year 2000. 12, 13, and 14. Okay, and then list 2 is the cases of measles in this case. So 205, 45, 195, and 625. Okay, then we're going to run a linear regression and a quadratic regression. So we're going to hit Stat. This is all just review. We're going to go over to Calculate, And then linear regression is number 4, as we've practiced. Hit enter a bunch. Right now we're not worried about storing it anywhere. And it gives you an equation. So I'm going to drag this over here. There we go. And then we'll just kind of leave it here for now, and then we'll come back in a second and we'll compare it to the quadratic one we get in a moment. Okay, so the procedure is the same to find a quadratic regression. We're going to hit stat, go over to calculate, and then we're going to use number 5, quadratic regression. So you can just hit 5 and then hit enter a bunch again until it spits out an equation for us. All right, there we go. Okay. And whoop. Nope. Don't want to draw on it. I want to move it. There we go. All right, so now we want to compare the two. The best way to compare the two is to look at the r values that you're given, and with a quadratic regression, you're actually given an r squared, so you could compare the r squared values. Remember, these are like a correlation coefficient, and the closer you are to either 1 or -1, the better your model is. So because we have a value almost exactly at 1 for that quadratic regression, we're going to say that model is the one that is most appropriate. Okay, so we're going to go ahead and write down what that equation is, filling in my A, B, and C. Y equals 147.5, I got some big numbers here, goes in front of my x squared, minus 3546.5 goes with my x, and then finally plus my C value, which was 21,367.5. Okay, what does the y-intercept of this equation represent? So remember, a y-intercept is your C value. So we're looking at that 21,365. It also happens when you have an x value of 0. And in here, x represents our years. So year 0 would be our starting year. It represents the number of cases, in this case 21,000, in the year 2000, or year 0 for this model. If we wanted to find the projected number of measles in 2021, we would just plug in an x value that's appropriate for 2021. And again, x represents years after 2000. So we would use an x value of 21. Okay, so we can just use our calculator for that. I hit 147.5 times 21 squared minus 3546.5 times 21 plus 21,367.5. And we get 11,939 approximately. Okay. Is this model reliable for the next 100 years? Well, let's see if we plug in 100, what happens? 100 squared minus 3546.5 times 100 plus 21,367.5. And we get a very large number. Let me drag that down for everyone here. Here we go. So we are getting that 100 years from now. What is that number? Let's see. It is, we have about 1 million cases per year. It says in 100 years, or 100 years from 2000, so I guess that would be the year 2100. There are approximately that many cases. So you can hopefully see wow, that's a pretty large number. It's a pretty large number of, what were we calculating here, measles. So to think that in 100 years we would have in a single year over 1 million cases of measles, that's, something's not ringing up right there for us. That's because we used a quadratic model, and our A value here was positive, which means if I made a rough sketch of this picture, it would look like this. So as my x values get bigger, if we use a quadratic model, there's no stopping it. It looks like it's almost growing. A word we use in math is exponentially. It's going to go up and up and up and up and up. And in reality, is that going to happen more than likely with measles cases? No, especially because that is a disease that really isn't around very much anymore. So we would say that no, it's not reliable, because this model will continue to increase without end. It's going to just keep going up and up and up forever towards infinity. So what would be more appropriate is maybe a different kind of model that would kind of level off or go back down at some point, and we'll talk about some of those later on in the course. Okay, that is the end of our 3.1 and 3.4 Big Idea session for Monday, March 1st. Again, office hours will be on Tuesday from 6 to 7 if you want to pop in and ask any questions about this. Don't forget to upload your solutions to the worksheet by 8 p.m. on Monday as usual. Feel free to reach out to me via email if you guys have any questions, and I will see you on Wednesday. Thanks, guys.